So anytime you're solving a problem with an absolute value, somewhere in your thought process needs to be the thought, what does absolute value mean? What does the absolute value of a quantity tell us about that quantity? And Jordan had a good way of thinking about it. What happens when you take the absolute value of a number? What does it really tell us? It tells you the distance of that number from 0 on the number line. So if I take the absolute value of, I don't know, 8, what am I going to get? 8. Because on the number line, 8 is 8 units away from 0. What happens when I take the absolute value of -3? Well, careful. So here I'm taking the absolute value of -3. So I'm measuring the distance of -3 away from 0. Yeah. Because -3 is 3 units away from 0. So what's the first thing that you notice about absolute values? What kinds of numbers do we get out of an absolute value? What kinds of numbers will a distance function spit out?
Positive.
Always positive or perhaps 0, but never a negative, right? We can never take the absolute value of a quantity and produce a negative answer. That doesn't mean that we can't put negatives into an absolute value. It's just that we always get non-negatives out on the other end. Because of its distance measuring property, right, that it measures a distance of a quantity from 0. Okay, so with all of that in mind, that's how absolute values work in a forward direction. What we're doing in this problem, and what you do when you're solving for x, is we're going backwards. Right? If my x is inside of the absolute value, my unknown is inside of the absolute value, we end up asking the opposite question, as we do, for example, here in this first problem. Absolute value of x is equal to 6. If we think of absolute value as measuring the distance from 0, this is saying what number, x, is a distance of 6 away from 0. So how would we answer that question? How did you answer that question? Here's my number line. Here's 0. I want to know what number is 6 units away from 0 on the number line. So 6 is one answer, right? It's one value of x. If I just have a measuring stick which is 6 units long, and I place one end of that stick at 0, then the other end could be at 6. So x equals 6 is one answer. What's another? -6. Because I made a choice in how to place my measuring stick down here on the x-axis, right, on the number line. I chose to place it so that it lied to the right of 0, but I could have just as well faced it to the left. If I go 6 units to the left of 0, I get another number which is 6 units away from 0, but because it's to the left of 0 on the number line this time, it's negative. So we end up generically, anytime there's an absolute value in our lives that we're trying to recover a variable x from within, we can expect there to be two different parts to our solution. Because when that absolute value sign goes away, what it leaves in its place is a sign ambiguity. In other words, when an absolute value sign disappears, it will always leave us with both a quantity and the opposite of that quantity in its wake. So we always get a plus version and a minus version whenever an absolute value sign disappears. In this example, we started with an absolute value equation. So it was absolute value of x is equal to something. So that's the first of our prototypes here. Absolute value of x is equal to whatever. That when that absolute value sign goes away, it produces for us two equations. The first of those equations that doesn't change the sign of the quantity that's on the right-hand side of the equal sign, and the other one where it exactly changes the sign. So x equals that thing, and x equals minus that thing. Sometimes, and this is not a notation that we're going to use much, but we will use it later in the semester, sometimes we'll write that using this plus or minus, this funny plus or minus symbol. That plus or minus denotes that there's a positive version of this thing, but we're also going to consider the negative version of this thing. That's the notation, for example, that becomes a part of the quadratic formula when we meet the quadratic formula way later in the course in Module 10. Okay. So we won't see it much, but this is the kind of example where it shows up. So all we needed to do in this first problem was just do that, make the absolute value sign disappear by splitting into two parts, one part with a plus, one part with a minus. Okay. So we get 6 and minus 6 for the first problem. So one of the mental traps that people fall into working with absolute values is the belief that because in these simple examples our answers were exact opposites of one another, 6 and minus 6, that's always going to be the case, that the answers, the x's, are going to be exact opposites of one another. And that turns out not to be the case for a reason that we're about to see. If I'm going to solve 3x minus 12 absolute value equals 3, what do I need to do first? What was your first step in solving this absolute value equation? So this is one idea. And I'm just going to pause right there and say, why wouldn't I be able to do that? Well, I'm going to argue that we can't just add 12 on both sides here. Why not? We can't add 12 to the thing on the left-hand side of the equation, because if I did, here's what I would get. I would get absolute value of 3x minus 12 plus 12 is equal to 3 plus 12, 15. And the problem with that, it's not incorrect. The problem is that the 12 on the outside of the absolute value and the minus 12 on the inside of the absolute value are prevented from getting together and canceling one another out, which is what we're hoping to do when we added 12. Right? When we're solving an equation for x, we're needing to reverse the order of operations. SADMEP, right? Not PEMDAS, but SADMEP. We're working, therefore, from the outside of the parentheses, and absolute value signs count as parentheses. They have the same grouping function that parentheses have. We're working from the outside in. So if I add 12 to both sides, that 12 is going to be stuck on the outside of the absolute value where it can't help us. So it's not that it's wrong, it just probably doesn't do what you think it does if that was the first step that you took. So instead, I'm going to agree with Tim that what we want to do here, the first step that we should take, is to attend to the absolute value. Make the absolute value go away, because in the reverse order of operations philosophy, we've done all of the addition, subtraction, multiplication, and division that we can do outside of the parentheses here meaning the absolute value bars. And so the next step is for us to somehow get inside those parentheses, make those parentheses go away, make those absolute value symbols go away. So it's time, the very first step in this problem, it's already time to make the absolute value disappear. And whenever the absolute value disappears, it creates for us two equations without absolute values in them. And the two equations it creates are given to us by this plus and minus principle down here at the bottom. So the first equation that it makes for us here is 3x minus 12 is equal to, and here I had 3, so just keep the 3 as it is. There's one equation. And the second equation it makes for us also is 3x minus 12, but it flips the sign on the right-hand side. In other words, it's saying, our original problem is saying, find me an x such that 3x minus 12 is 3 units away from 0. So if 3x minus 12 is 3 units away from 0, that means 3x minus 12 could be 3, or that 3x minus 12 could be negative 3. So we've now split it into two separate equations. And each of these equations, because it doesn't have an absolute value bar, we know how to solve each of these equations separately, based on what we remember from Module 2, which is then what we do. What do I have to do to solve each of these equations? Add 12 to both sides. That works for both of these equations, by the way. The first equation then becomes 3x equals 15. Second equation becomes 3x equals 9. And then the last step to get x by itself, divide by 3. And so the two solutions that I get for that equation are x equals 5, x equals 3. So this method produced for us two answers, just like in the first problem. But the answers, the solutions that we got for x, were not opposites to one another, right? 3 and 5, rather than 3 and minus 3 or 5 and minus 5. So just because we get plus and minus the same quantity when the absolute value signs disappear is no guarantee that our final answers for x will be equal and opposite the way that they were in the first example here. So just be cautious about that. Any plus and minusing that you do should happen exactly at the time when the absolute value bars go away, which in this example happened immediately, and then after that we had to do some additional algebra to unwrap the x.